we've been working with surfaces where z is described as a function of two variables, and we can think of x and y as the inputs and z as the output, and we can describe that surface. But if we move all of the pieces to one side, if we just say z minus whatever that function of x and y is equal to 0, we can then define a three-dimensional function, f of x, y, z, and we know that that function will always be equal to 0 by definition. So this is really equal to that. So an example of that would be, instead of having a paraboloid of z equal x squared over 3 minus y squared plus 1, we can instead write that with everything on one side, z minus, well, this is a minus 1, z minus x cubed over 3 plus y squared minus 1 equals 0. And the question might be, why would we want to do that? Well, the reason we want to do that is because if we do, we can develop some interesting results. If you take a look at this, this is an elliptical paraboloid, so it's actually different from that. But this elliptical paraboloid, if I think about some point on the surface, I can think about an idea of a tangent plane. So think if I had like a Post-it note or an index card maybe, I could touch it to exactly one point on the curve, and that would be what we call the tangent plane. So this little purple line you may not be able to see is a tangent line, and this other purple line is the normal line. And if we go all the way back and remember our equation of a plane, the equation of the plane takes a normal line, takes the components of a normal line, and then multiplies them by this vector. So this vector, which is defined in the plane, it dots it with that. And that creates an equation that's equal to 0 because the normal line is normal, so it's orthogonal to every vector in the plane. So we know that if the vector's in the plane, the normal line dotted with that is going to be equal to 0. But anyway, so I'm kind of around all over the place in terms of the words here. But the whole point that I want to make is that we have this idea of a gradient. And what we find is that the gradient is actually normal to that surface if the gradient is defined in terms of all three variables instead of just being the gradient of the function of two variables. Because again, if it's the function of three variables, it's normal to the surface. So since it's normal to the surface, we can use that to construct the equation of the plane. So we go through this. We have a vector in the plane. We know that the gradient's normal. We can remember the equation of the plane is the components of the normal line multiplied by this, or dotted with this vector in the plane. And so we can go all the way down and realize that if we take the gradient and dot it with this type of vector, or if we use this terminology, the partial with respect to x times x minus x0, partial with respect to y times y minus y0, plus partial with respect to z times z minus z0. If we fill that out, and notice that these are evaluated at a specific point, if we fill that out with all the values, we have z0, y0, and x0, then we will generate an equation in the plane, and we're going to do some examples of just that.